So in this video, we're going to begin looking at Section 8.5, which covers amortized loans. Amortization is the process of paying off a loan plus interest by making a series of regular equal payments. An amortized loan is a loan that is paid by amortization. So here we have a formula for amortized loans. Assume you borrow an amount P, which you will repay by taking out an amortized loan. You will make M periodic payments per year for N total payments, and the annual interest rate is R. Then you can find your payment by solving for R in the equation. P times 1 plus R over M raised to the N power equals R times 1 plus R over M raised to the N power minus 1 over R over M. Now both sides of this formula should look familiar to you. The left side is the formula for finding compound interest. So this gives us the future value of a lump sum that is receiving compound interest. And if you look at the right-hand side, this is the formula for finding the value of an annuity where you're making a payment of R for a period of N times. So here's basically the deal that's going on with an amortized loan. If you borrow money, say you borrow like $100,000 to buy a home, well, when the bank gives you that $100,000, they're looking at that as a compounded interest problem because they want to get interest on their $100,000. But your perspective, you're looking at that as an annuity. As you start paying back the loan, then you're making equal payments each month. And so you're looking at that as if you're paying into an annuity. So the point where the compounded interest and the annuity are equal is going to be what the payment needs to be. And so that's why we have this particular formula. So again, the future value of compound interest equals the future value of an annuity is where this formula is coming from. Let's take a look at an example, and that will hopefully help make this make a little more sense. So take a look here at example 1. A recent retiree has taken an amortized loan for $95,000 to buy an RV. The yearly interest rate is 8.4%, and the retiree agrees to pay off the loan in 10 years. What is the monthly payment? Well, so to figure out the monthly payment, we're going to use our amortized formula, which is this formula here. So we need to figure out what the monthly payment is, which means we need to find R. So our question here is asking, what should R be? So that means we need to figure out the rest. So first of all, the principal, the amount that was borrowed, is $95,000. So P equals $95,000. The interest rate is 8.4%. So that is going to be 0.084. We are making monthly payments, so that means we can assume that we are compounding monthly. We're going to pay it off in 10 years, so the time is 10 years, and so that means N is equal to 12 times 10, which is 120. So we're going to make 120 different payments. So if we fill these values into our formula and solve for R, that will give us what the monthly payment needs to be. So filling it in, the principal is $95,000, so $95,000 times 1 plus R, 0.084 divided by M, 12, and that gets raised to the 120th power. That is going to equal R, which we need to figure out what that is, times 1 plus 0.084 divided by 12, again filling in my percent in decimal form, divided by 12 because we're compounding monthly, and that gets raised to the 120th power, minus 1 over 0.084 divided by 12. Now this looks like a pretty terrible formula, but when you look at it from the perspective of this is just the compound interest formula that we've used, and this is just the future value of an annuity formula that we've used, it's really not that bad. And so what I have is this is going to just be a number, and that equals r times this number, and so we can solve. We just have to figure out what those two numbers are. So cleaning up both sides a little bit, let's figure out what 0.084 divided by 12 is. 0.084 divided by 12 is 0.007. So this right here is 0.007, and so 1 plus 0.007 is going to be 1.007. So I have 95,000 times 1.007 raised to the 120th power. That's what I have on the left. On the right-hand side, again, 0.084 divided by 12 is 0.007. So I have r times 1.007 raised to the 120th power, that's what I have right there, minus 1, divided by, again, 0.084 divided by 12 is 0.007. So that's what I have right there. So let's figure out what this left side equals. So bringing back in my calculator, 95,000 times 1.007 raised to the 120th power. So that is 219,411.8462. So 219,411.8462. Again, I don't really want to round that because I don't want rounding to cause problems for me. And that's going to equal r times. Now I need to figure out what r is times over here. So I'm going to, again, pull my calculator back in. Move that to the right so I can see. On the top of that fraction, I have 1.007 that's being raised to the 120th power, and then minus 1, close parentheses. So I put the top of the fraction in parentheses, 1.007 to the 120th minus 1, that's in parentheses, and then I'm going to divide that by 0.007, and so that is 187.085483. So this is 187.085483. So if I divide both sides by 187.085483, that'll give me the answer. So again, r now is just going to equal the $219,411.8462 divided by 187.085483. So 219,411.8462 divided by 187.085483. That is equal to $1,172.79 if I now round here at the end to the nearest penny. So that's going to equal $1,172.79. So this retiree will have to pay $1,172.79 each month for the next 10 years to be able to pay off the $95,000 loan for the RV. Now look at example 2. Example 2 says, construct an amortization schedule for the first 3 payments on the loan from example 1. So to construct an amortization schedule means that we want to figure out what the payment is each month and then what the interest is that's been paid on that amount, how much principal was paid, and what the balance still is. So for example, if maybe after say 4 years' time the retiree wanted to pay off the loan, then how much would they still owe? How much has been paid in interest and how much is still owed on the principal? So if the way we do that is we're going to just do the first 3 payments and figure out what the balance is. And so this is, again, the beginning of the amortization schedule. So for the first month, the retiree is making the payment of $1,172.79. Now, how much of that is going to be going towards paying the interest? Well, to figure how much interest has been paid, we're just going to use the simple interest formula. Interest equals principal times rate times time. And at this point, the principal is $95,000 because nothing has been paid off at this point. So we're going to take $95,000 times the interest rate, which is 0.084, times the time. This is a 1-month period, so that is 1/12 of a year. So that's what we're doing here. So if I bring in my calculator, 95,000 times 0.084 times 1/12, that is $665. So $665 is going to go towards interest. So that means if I take the $1,172.79 and subtract the $665 that's going towards the interest, $1,172.79 minus the $665, that is $507.79. That is going towards the principal. So that means now, if we take the $95,000 amount of the loan and subtract off the $507.79, 95,000 minus 507.79, that is $94,492.21. So $94,492.21, that is the amount that would still be owed. So if after 1-month period, if the retiree wanted to pay off the loan, he or she would have to pay back $94,492.21. So we're going to continue this. So for the second payment, the payment would be $1,172.79. Now, at this point, we only have to pay interest on the balance that's still owed. So we would have to pay interest on the $94,492.21. So I'm not going to write this down. I'm going to just bring back in my calculator. The principal is $94,492.21. And so if I take that times the interest rate, 0.084, times the time, which is 1/12 of a year because it's a monthly payment, then that is $661.45 if I round to the nearest penny. So $661.45 of the second payment is going towards interest, which means $1,172.79 minus $661.45, $511.34 goes towards the principal. So $511.34 of the second payment goes towards principal. And so now if I take the $94,492.21 and subtract off that amount that goes towards the principal, so $94,492.21 minus $511.34, that is a balance still of $93,980.87. So after the second month, we still owe $93,980.87 on the loan. So at that point, if the retiree wanted to pay off the loan, he or she would have to pay off $93,980.87. One more month. So for the third month, if we make our payment of $1,172.79, then the interest for that month is going to be our balance, $93,980.87, times our interest rate, 0.084, times time, 1/12 of a year. That is $657.87 if I round to the nearest penny. So $657.87 of this payment goes for interest, which means $1,172.79 minus the $657.87. That is $514.92 goes towards the principal. So if I take the $93,980.87 and subtract this, then that will be my balance. So $93,980.87 minus $514.92, that is a balance now of $93,465.95. So after my third payment, we would still owe, or the retiree would still owe, $93,465.95. So if the retiree wanted to pay off the loan at that point, the payment would need to be $93,465.95. And so that finishes this example. We've completed our first three payments on the schedule, but we could also continue that for the entire 10-year period. Now, typically, we wouldn't do all of that by hand. Instead, we would do that in a spreadsheet. So I just want to bring in, I completed a spreadsheet for this. So here we have our $95,000 balance at the beginning of the loan. And so for our first payment, again, I did this on a spreadsheet. We made the payment of $1,172.79. And so $665 went towards interest, $507.79 went to principal, and so the balance after that first payment is $94,492.21 as we calculated. Similarly, for the second payment, we make our payment, $661.45 goes towards interest, $511.34 goes to principal, $93,980.87 is the balance at that point. Third payment, and so on, and so on, and so on. So, for example, after the 30th payment, $78,114.11 is still owed at that point. And what I want to point out is, as we make the payments, because we're paying a little bit towards the principal, at first, a very high amount, more than half of the payments going towards interest and less than half is going towards the principal. But as we go down this sheet, as we go, more and more is going towards the principal and less is going towards the interest. So here we go, here's payments 31, like here's payment 60. So at that point, $766.34 is going towards the principal and only $406 is going towards interest, and so on. If I bring in a continuation of that, so as we get to the end, our 120th payment, well, that payment, only $8.15 was going towards interest, and most of it was going towards the principal. So we ended up paying it off at the end of our 120th payment. But again, along the way, with this amortized loan, if someone decides they want to pay off a loan, then they can figure out what that amount would be at that particular time. And typically, when an amortized loan is made, such as we might do this for a car payment, or we might do this for definitely a home payment, then you would be given an amortized schedule from the bank that would tell you exactly this information that we've just figured out. There are also calculators that you can find online that would figure out these schedules for you. But we could do it with a spreadsheet as I've done here. Let's move on to another example in the next video.